All right, several chapters, lessons ago, we learned about particular solutions and complementary solutions. So I'm gonna give an analogy similar to that, where we're going to talk about ordinary points and singular points of a differential equation. So we define a point to be ordinary if the coefficients of a differential equation of second order follows this format here. So here's our general format. And so if p of x and q of x are in standard form, then we define that ratio of those starting functions to be p of x and q of x. And so the ordinary point solutions are anywhere where this leading function does not equal 0. So that one right there. A point that is not ordinary is defined to be singular. So that would be this other definition here, where that leading function of x in front of the second derivative, if it has a solution of some type, that solution itself we refer to as a singular point. Okay, so this might be a little bit easier if we jump in and look at an example. Okay, so in this differential equation here, this x squared minus 1 y double plus 2x y single plus 6y equals 0, we're looking just at that x squared minus 1. So anywhere at that x squared minus 1, which is going to be plus or minus 1, we define those x values to be ordinary points. So I'm sorry, the positive and negative 1 would be considered singular points, and anywhere else would be considered ordinary. Okay, let's take a look at another example. So in this one, we have x squared y double plus y. So if I'm just focusing on the x squared, setting that equal to 0, that says that x at 0, so that one solution would be considered a singular point. And lastly, x squared plus 1, blah, 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 all that other stuff. So if I set that equal to 0 and solve, I'm going to get complex. Whereas all the other solutions would be considered ordinary points. And as one might suspect, there's a reason why we are bringing power series into this, and that's because we're going to use that to solve differential equations. So if I have an ordinary point about a differential equation, I can always find two linear independent solutions from the power series, meaning the function looks something like the given generic form for a power series. And that power series solution converges for at least some interval defined by this absolute value, so distance mean x minus x naught less than r, where r is the distance from x naught to the closest singular point. So I want to emphasize that because we've just defined that term. So when we start talking about singular solutions, it's like, why are we talking about this? Well, that's because this theorem guarantees that we're going to have a solution where that distance to the singular point is defined by that radius of convergence. So a solution of the form given in that summation is said to be a solution about the ordinary point, and the distance r is the minimum or lower bound for the radius of convergence. Okay, so let's do a little bit of practice just talking or identifying that radius of convergence around certain ordinary points. All right, so in this one, we're given the x squared minus 2x plus 5. And since we're trying to find a solution around a specific point, it'd be good to know what our singular solutions would look like for that function. So we want to solve for x, and that's not factorable. So Square root of negative 2 squared minus 4ac all over 2a. All right, so that looks like 2 plus or minus 4 minus 20, so negative 16. So 2 plus or minus 4i over 2, which is 1 plus or minus 2i. Okay, so the singular points would be 1 plus or minus 2i. And just kind of remind us real quick, on a complex plane, that would look like, let's see, so we're going over 1 unit and up and down 2i. So this would be 1 plus 2i, and this would be 1 minus 2i. Okay, and so because x is 0 for this ordinary point that we're trying to find a solution, or this radius convergence around, then we know there's got to be 2 solutions centered around x equals 0. So that means we're looking at the distance from the origin to those points. So the distance just means find the magnitude of those individual vectors. So I'll just find the magnitude of one of them because they are symmetric. So that would be square root of 1 plus 2i squared, which is the square root of 5. Okay, so that tells me that the distance from the origin to those points would be square root of 5. So that means our solutions must converge at anything less than square root of 5. So that's our minimum radius there. Additionally, what else can we say about the types of solutions that this type of function would look like? If we go back up to our theorem, we've got that general statement that y equals a summation from n equals 0 to infinity of Cn x minus x naught to the n. So in this case, our x naught is at 0. So that means our solutions are going to look something like this. Okay, so how does that change when we look at centered around an ordinary point of negative 1? Let's scroll this up a little bit. Okay, so because we're now centered this around x equals negative 1, we actually can get a sense as to what our solution is going to look like, because I can replace that x naught with negative 1. And then we'll go talk about our radius. So they're all going to look like x minus a negative 1 to the n. So I'm just going to clean that up real quick. C of n, x plus 1 to the n. Okay. And as far as our radius, then, our distance, so let's go back to, instead of being at 0, now we're at negative 1. And we still have this at 1 plus 2i. And 1 minus 2i. All right, but I want to figure out this distance here. Again, it's uniform for both those vectors, so it's not too bad. So I'm going to do a little Pythagorean Theorem action here. So that's 2 units over and 2i up versus 2i down. So the radius would be 2 squared plus 2i squared, which is 4 plus 4, which is square root of 8, or 2 square root 2. So our power series would converge as long as the absolute value of x plus 1 was less than that radius that we solved for, so 2 square root 2.